Got it? All right, excellent. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for this opportunity just to study advanced calculus. Just pray that you'd just give us understanding and just help these students, Lord, to glorify you in what they do this semester, Lord, that they would work not for their own grades or benefit and so forth, but for your glory, Lord. In your name I pray. Amen. Okay, so I have written some notes, and there's a book we'll eventually use. I don't know if I brought it today. Nah, I don't have it with me. Eventually we'll use the book that I required, but it'll be a few lectures till we get to that. For the moment, I'm trying to develop the calculus over a normed linear space. So if you haven't had linear algebra, that's unfortunate, but Travis will follow along. He'll be okay. It's going to be rough for a few lectures, by the way. I mean, don't despair. It's going to be rough. Okay. So I can give you the email of a previous engineer who survived this despite, not having a bunch of math background. I like having engineers in here. It's fun. So I'll start with linear algebra. All right. So our essential examples we need are Rn, which you guys know, right? N tuples of real numbers. So that's one of our examples. Second example, are m by n, set of n by n real matrices. So some people would use this notation like Aij to indicate an array, right? Such that 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n. Right? These are the m by n real matrices. Now, this list I'm assembling here, these are examples of what are called vector spaces, right? Because you can take two objects in these sets, add them together, and you get another object of the same type, right? And there's also a notion of scalar multiplication. Here, I'll remind you, this is really shocking. X plus y is defined to be x sub I plus y sub I. Check it out, vector addition. And Cx I is C times x sub I. So this is, this defines the vector space structure in Rn. Of course, this is the quintessential example of a vector space, really the most important example. And the definition for vector addition and scalar multiplication for m by n matrices is much the same, right? I mean, I probably shouldn't even write it down today, but I can't help myself. A plus bij is equal to, so we add component-wise, right? And we scalar multiply component-wise. Right, so this defines, I say vector addition and scalar multiplication, but that terminology might be foreign to you, Travis. When we talk about a vector in linear algebra, a vector is just something you can add. So it doesn't, a matrix is a vector. A function can be a vector. We talk about abstract vector spaces. No, we would use the term like geometric vector for a vector vector. Or I guess we could use the term vector vector. I think you got a good term. It's not a bad terminology. Now, notation here that's important because we like to work a lot of homework problems and stuff on matrices. So let's make sure we have the appropriate notation to deal with problems that we face. So of course, on the one hand, you can write it all gory and like this, right? This is almost always the wrong way to think about your problem, right? You can also look at the matrix as being columns concatenated, like column 1. And concatenate is just a fancy word for glued together. My brother says I shouldn't use the term concatenate in this sense because it has a more technical meaning and this is not appropriate. But I say concatenate because I read it in a book somewhere, so it must be right. But then again, just because somebody writes it in a book doesn't mean it's, I don't know, glued or concatenated, you pick it. So you can either look at it as a stack of columns or a stack of rows. I mean, this way. There are n columns, right? There are m rows in an m by n matrix. And the other interesting thing that's available for matrices, which is not so much available for vectors and these kinds of vectors, is multiplication, right? If we have appropriately sized matrices, we can say ABij is equal to the sum k equals 1 to, let's say, n of aik bkj. This is assuming that here A is an element of, let's say, Rm by n, and B is an element of Rn by p, let's say. So you can multiply matrices in this way, right? It's the standard formula. For what it's worth, this is equal to what? This is equal to row I of A dot product with column j of B. That makes sense because we can look at the rows of A as n-dimensional vectors, and we can look at the columns of B as n-dimensional vectors. So taking the dot product of an n-dimensional vector with itself makes sense. But admittedly, that dot product is sort of a hybrid. I'm taking the dot product of a column vector with a row vector. So if this is bothersome to you, there's various things we could do, like, let's see here. What's the size of the row vector? Well, the ith row is what? It's 1 by n, right? This is a 1 by n, and we're taking the dot product with a what? By n by 1, right? The jth column is an n by 1 matrix. The jth column of B is n by 1. Right, if we wanted to be, so which one should I transpose? Yeah, the column, yeah. So if you're a purist and you insist that we actually have a matrix formula for it, if you define, I mean, it's somewhat circular here, right? Because you're like, well, I had already defined the dot product of column vectors, or the row column product. I don't know, whatever. Let's not get into the weeds too much. I've already spent too long on this. Next example. My point is we have matrix multiplication, addition, scalar multiplication. Great. Cn. Cn is the set, as you might expect, of n tuples of complex numbers. All right? And guess what else? Yep. We can talk about n by n complex matrices. I mean, I don't know what's the right notation. These are m by n arrays of complex numbers, all right? I don't want to belabor it. And you define addition and matrix multiplication just the same way for complex matrices, right? Now, these form real vector spaces. I mean, it's also true that these form complex vector spaces in the sense that you can scalar multiply by a complex number. All right, fine. And then example 5, we can talk about if V and W are real vector spaces, all right, then now in the notes at the moment I've written Homer. This is homomorphisms from V to W. I probably am going to err on the side of using the following notation instead, though. So what I mean is linear transformations from V to W, right? W-valued transformations. The linear transformations, that also forms a vector space structure, right? You can add maps. You can scalar multiply maps by pointwise addition, pointwise scalar multiplication, right? If we also talk about the endomorphisms of V, so that would be the linear transformations from V to V, right? That's another example of a vector space, but that's actually also what's called an algebra, because we can also take two such transformations and compose them and get yet another transformation. So if I take two linear transformations from V to V and I compose these endomorphisms as they're called, I get yet another endomorphism, right? So this guy, if I have, T1 and T2 in the endomorphisms of V, I have the following nice things. I have T1 plus T2 is defined. I have that C times T1 is again an endomorphism, right? The sum of linear transformations is a linear transformation. The scalar multiple of a linear transformation is a linear transformation. But one more thing, the composite of linear transformations is a linear transformation. So this together makes the set of endomorphisms special. In fact, it has what's called an algebraic structure. It's a vector space together with a multiplication. So just a little terminology. A lot of the homeworks, some of the more interesting homeworks I've given you guys this semester will involve what I call GLV. GLV, what's this? Well, this is basically, we're looking at phi in the endomorphisms of V, right? So in other words, it's a linear transformation from V to V such that what? Phi is a bijection. So this is the set of invertible linear transformations, right? The general, what's called the general linear group on V. Don't worry, I'm not going to test you on group theory in here so much, but it's just useful terminology because that is what it is. It's a group in the technical sense. Now, more special than this, we like to work a lot with these guys, GLN, GLNR. Now, this actually is, this is here A in n by n matrices such that the determinant of A is not equal to 0 is a convenient definition. You could also say these are the invertible matrices, invertible square matrices with real entries, right? Now, these are exactly the matrices which will appear as the standard matrices of bijective endomorphisms of Rn. All right. Anyway, I think I've said too much. So these are standard examples. We can get a lot of mileage out of just these examples. All right. Now, moving on. I think I've already violated my pace for this course. Yes, I have. So what do we need to know about linear algebra in a nutshell? I mean, those are some examples of vector spaces. This is not, I mean, this GLNR thing is not a vector space, right? Is the sum of invertible transformations invertible? I mean, is the sum of invertible matrices invertible? No. Identity matrix invertible minus the identity matrix invertible. Add them together, get the zero matrix. Is the zero matrix an invertible matrix? No. So, you talk about invertible transformations, that doesn't have a vector space structure, but it's something interesting in the realm of vector spaces, right? What makes these interesting is that if you take an element of GLV, it will take a basis for the vector space and map it to another basis. In fact, any two bases for a vector space are connected by such a thing. But now I'm getting ahead of the story. So of course, we like to talk about what? The span of a set, right? So what's that? C1, S1 plus plus CK, SK, such that S sub I is in S and K is in the natural numbers. So I allow the possibility that S is infinite, but the span is always the set of all finite linear combination of vectors from S. In the case that S is finite, you can just take linear combinations the same size as S without loss of generality. But I'd like to define things like span of a set of polynomials, right? So the point is you can add together 3 of them or 5 of them or 10 of them, or however, whatever. That's a span. Span is, of course, interesting because this is a linear combination, right? terminology, linear combination. Oh, what did I not say that's important? Where are the C's, right? Yeah, C1, C2, where are they in? The reals, okay? I'm focusing on real vector spaces in here. In my linear algebra course that some of you took, we did a lot of other fields. We took complex vector spaces. We talked about vector spaces over a finite field even a little bit. But for our purposes in here, I'm going to be focused primarily on real vector spaces. So if I talk about a vector space, assume it's a real vector space if I don't say otherwise, all right? And so likewise, in our theory of spans and so forth, if I talk about span, I'm really talking about a real linear, instead of all finite real linear combinations, okay? Now what makes the span interesting is we have this theorem, right? If you take the sum of two linear combinations, what do you get? You get another linear combination. If you take a scalar multiple of a linear combination, what do you get? Linear combination, right? So it satisfies what's called the subspace test. In fact, this is going to be a subspace of V. So this is subspace. A subspace is just a vector space. It's a subset of a vector space, which is again itself a vector space subject to the same operations as V. So the span gives us this like natural way of building subspaces, right? In calculus 3, we already thought about this. We have like the direction vector to a line. The span of the direction vector gives the line, right? If you got a pair of tangent vectors to the plane, if the plane goes through the origin, then the span of those forms out the plane, right? So this idea of span is already present in calculus 3 if you're looking for it. Now, but also important is the sort of the idea of a minimal span. Like how can I make S as small as possible and still get the same geometric object, right? And that's where linear independence comes into play. Linear independence, S linearly independent, only if whenever C1 S1 plus C2 S2 plus da 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 plus CK SK equals to 0 for S1 S2 da 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 SK and S implies that C1 equals to C2 equals to da 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 equals to CK equals to 0. We referred to this as Kang's definition last semester's linear algebra. It is a good definition. It basically says a set is linearly independent if whenever you take a linear combination of those vectors and you get 0, it must itself be the trivial combination. You've done nothing more than 0 times the first vector, 0 times the second vector, 0 times all the vectors, it gives you back 0. Well, hooray. In other words, there's no interesting way to see one vector in S as somehow built from other vectors in S under linear combination. Now, if we're working over a field, as we are, that also means that you can't write one of the vectors in S as a linear combination of the remaining vectors. However, this definition of linear independence we just gave is equally well placed for modules. So it's to be preferred. In modules, you can have linear dependence, where it's not possible to write one of the vectors as a linear combination of the others, and yet there's linear dependence. This comes from the existence of what are called zero divisors over a ring. That is a comment well outside the scope of advanced calculus I just made. My apologies. Sorry. I should behave. I'm sometimes asked, how does research influence your teaching? It hurts it sometimes because it puts things in my mind I shouldn't say right now. All right, anyway, that's linear independence. What happens if you've got a set which is both linearly independent and a spanning set? Right. Beta, subset of V with the span of beta equals to V, and beta linearly independent is a basis for V, right?
And we could replace that subset with proper subset, right? Because it has to be.
Yeah.
We're talking about the, like, just the origin.
Yeah, I guess there's the.
But then it would be an F.
Yeah.
Yeah, then the beta would be an set, so it would still be
It's probably not harmful to do that, yeah. But, it's like every day I drive a Honda Odyssey or a Lamborghini to school. It's true. I was watching some YouTube videos about like the Bugatti supercar versus the other ones. There's amazing YouTube videos.
Did they race it against a Tesla?
It's a Tesla. Let's see here. Okay, I digress. Oh, yes. So furthermore, the number of things in beta is called the dimension of V, right? But typically, I want this to be, supposing that this is less, I'm muddling it, I'm sorry. You can talk about dimension in terms of cardinality, all right? The dimension of the space can be the cardinality of the space. This is still true for like infinite dimensional vector spaces. So there is a notion of dimension that is beyond the finite, but that's not really important to our purposes. Yeah.
Is the S necessary to be finite? I mean, linear independence.
Well, in an infinite dimensional vector space, you could have an infinite basis.
But
I mean, you have to have an infinite basis.
like the linear independence still useful, like just finite combination?
Yes, still finite linear combinations, right? But that's an open. That's where you get into different notions of infinite bases. Some people deal with. You see there's some window for different ways of thinking there, right? Are you thinking about finite linear combinations, or are you going to start thinking about
Finite linear combination and infinite linear combination.
or finite but what do you mean by a finite infinite combination? Maybe you.
I mean, just either finite linear combination or infinite linear combination.
What would an infinite linear combination be?
Just like similarly to a free algebra.
Right. Then the question is, do you want to insist on that, or do you want to insist on, or do you want to insist on the ones where the norm is finite or something? I think there's different ways of thinking there.
Could you define it as like a series of vectors such that a series converges?
This is something you could think about. But anyway, we fortunately won't go down that path here. Yeah. But I'll talk more to you guys about that. So let's say if the number of things in beta is less than infinity, okay? In other words, suppose that the basis, you have a finite basis, then the number of things in the basis is called what? The dimension of V, right? Moreover, if we have beta is equal to, V1, V2, Vn, then if we have x is equal to, say, x1 v1 plus x2 v2 plus xn vn, then the coordinate vector of x with respect to the beta basis is x1, x2, xn. All right. This is the coordinate with respect to the basis. I'm still giving you guys entirely too many details. Curses. All right. My other notation for this is sideways TIE fighter sub beta of x. So this phi beta is the so-called coordinate map. It goes from V to Rn for an n-dimensional vector space. All right. That's it, pretty much, for linear algebra. We have a place where we can add vectors, we can scalar multiply, we look at spans, we look at linear independence, we look at bases, and we try to study the property of how these things relate under linear transformation. That's pretty much what linear algebra is. Now, I guess the next question you should ask is, okay, so what is the basis for each one of my examples? Right? Can I state a basis for each one of the examples we've done so far today? What would that basis be? So I'm going to extend the terminology of standard basis a little bit past what I do in linear algebra to introduce like a standard basis. I'm going to say that there's kind of a standard basis for these At least the first two examples, right? I mean, the first one is actually what I usually call the standard basis. Right here, definition. Oh, man, come on. Sad. Definition, oh, man, it's not much better. EIJ is equal to Kronecker delta IJ. Do you guys know what the Kronecker delta is? Let me tell you. This is 1 when I is equal to j, and it's 0 otherwise. All right? It's kind of like the direct delta function for you, Travis. In fact, the direct delta function is named that because it's like that. This is historically before the direct delta function, and it's why the direct delta function is called what it is. Same idea. But this is finite. So, I mean, this is, so, all right, so like E1 is 1, 0, 0, right? And E2, 0, 1, 0, and so forth. En. These are column vectors. It's just my notation to write them as this, you know? All right. If I want an honest-to-goodness row vector, I write this, guys, right? So that would be equal to En transpose as a point of order. It's easy to prove that those form a basis for Rn. They're linearly independent. They span. Great. Now, for the matrices, we can use these so-called matrix units, Eij. And in fact, for the standard basis for Rn, what's the coordinate vector of what's the coordinate vector of this? What? Just itself, right? Yeah, so phi beta of x is just equal to x again. So in fact, the Cartesian coordinate system, the coordinate map is the identity map on Rn. It's rather boring. Fine. For example 2, it starts to get a little bit more interesting. Eij, KL, we're going to define to be Kronecker delta IK, Kronecker delta JL. These are the so-called matrix units. For example, let me just do the 2 by 2 case. So 2 by 2 case. You have E11, 1, 0, 0, 0, E12, 0, 1, 0, 0, E21, 0, 0, 1, 0, and E22, 0, 0, 0, 1. Now, the other thing that I should have said already, but oh well. Basis has an ordering. We think it's not just a set of vectors, it's an ordered set of vectors. So that's important because otherwise the coordinate wouldn't be well defined, right? Like the order of the vectors in the basis matters to the definition of the coordinate system. But this is the so-called standard basis for m by n matrices. We just use Eij with the sort of standard lexicographic ordering, which means that you go across row by row until you exhaust all the rows, right? Here, let me just take a breath and ask you guys, what's the coordinates? So if I use my, if I say that this beta is equal to, E11, E12, E21, E22, right? 2 by 2 matrix. Then I can ask you, what's the coordinate if I take phi beta and I act on the vector matrix 0, 3, 7, 9, what's the coordinate vector there of that matrix with respect to the standard basis for matrices? 0, 3, 7, 9. Very good. So there are various things you might try. I mean, you could either, so basically what it says is you list the rows out one after the other in a column. That's the standard coordinate system. There are other ones optional. If you study matrix theory more deeply, some people take the vector, and like list out column by column in a string. I mean, you got options here. If you want to see a very, very deep and masterful look at those kinds of deliberations, you should look at Gullub. This is a very popular graduate level numerical linear algebra text that is deep. You can get a decent copy from India for about 20. So thanks to Beilu for pointing this book out to me. If I fully absorbed this book, I would know all kinds of secret formulas. All right. I'll let you read the notes. We can also find a standard basis for Cn and Cm by n. I'll tell you what, I'll just do it, rather than state it in general, I'll just go ahead and give you an example for C. Let me just do the 2 by 2 complex case rather than doing it in general so you guys will understand better, I think. So we could look at C 2 by 2. There are sort of two natural, let me just, what does a typical thing in here look like? It looks like this, right? It's like A plus IB, C plus ID, E plus FI, G plus H. Phew, I was worried I was going to run into I. Okay, good, we're good. And the thing is, if you take this 2 by 2 complex matrix, right, you can write it out like this. This is A times 1, 0, 0, 0, plus B times I, 0, 1, 0, 0, 0. Right? I get sick of writing those, so how about this? C times E12 plus D times I E12 plus E times E, I'm going to regret this, plus F, why did I do this? E21, sorry, plus G, I'm regretting. That was 2, 2. All right, so there's your 2 by 2 complex matrix. I've written it as this linear combination of these 8 matrices, as a real linear combination of these particular 8 matrices, right? So one basis you could choose, beta, would be like this, right? E11, IE11, E12, IE12, E21, IE21, E22, IE22, right? And if I use that as the basis for complex 2 by 2 matrices, what's the coordinate vector of my my matrix? Let me call this thing Z. What's phi beta of Z with my setup here? Oh yeah, sorry, it's kind of boring. So A, B, C, D, E, F, G, H. All right, it's almost like I planned that. Okay, yeah. Now there's another very popular, the other popular way to do the, I mean there's choices in the complex case. When you're looking at a set of complex matrices as a real vector space, there's sort of two usual choices. This is one of them. The other is to, let me call this thing Pac-Man. All right, let me call my last example. Well, this was example 1, wasn't it? This is example 1, isn't it? It's the first example I've given in here. It's an odd place to start with the example. This is example 2, right? So I can refer to them. But if you take example 1, right? If you take the example 1 basis, Pac-Man, and then you union it with I times Pac-Man, you could call this thing gamma. Although I haven't checked my notes, I may have used beta and gamma in the opposite sense in the notes. If I have, my apologies. 50-50. This is another usual basis that you could use for 2 by 2 complex matrices. With respect to this gamma basis, what would the coordinate vector of Z be? So what it says is I just do all of the basically I take this term, this term, this term, and this term first, and then I put all the I multiples last. So, goodness gracious. Oh. A, C, E, G, what's that? B. What's that? B, D, F, H? Thanks, guys. So you go, there's the other. Now, Yeah, that's ordered union. Don't ask me for the set theoretic justification of that. Now, like up here, you could take the standard basis, right? You could take EI, maybe let's say EJ, union with IEJ. That would give you a basis for Cn, right? And if you looked at the coordinate vector, if you had a typical vector in here that was like x plus iy, where x and y are themselves real n-dimensional vectors, then with respect to this coordinate system, it's just x, y like that. Whereas if you use the staggered basis where you have basis, then I times basis, then what it looks like is it's like real part, imaginary part, real part, imaginary part, real part, imaginary part, real part, imaginary part, listed out like this. So you got these two choices. They each have their own set of benefits. All right, I've said entirely too much about that. Let me go on. Sorry. All right, so that was supposed to be 10 minutes. Ah! All right. It's a little bit bad. Don't worry, I'll make up for it by skipping proofs. Let's see here. Now, I should be careful what I erase because I will regret it. So that brings us finally, to something interesting. Don't worry, this will pay off. I mean, it's good. It's important for us to go over notation. Otherwise, we'll always be like, what do you mean by that? Although that's not entirely truthful because most of you know what I was talking about already. So I just wasted your time. But yes, we're having pity on the newcomers. Let's see here. Definition, normed linear space. Finally. Now we're finally getting into something that's actually more about really the meat and potatoes of what I'm getting after here today. So we'll say NLS for normed linear space. So for us, a normed linear space will be a real normed linear space. It's going to be a real vector space, all right? With a function which we usually denote by these bars like this. So it goes from V to the reals. All right? And it has these properties. Here are the properties that it has to have. 1, the norm of Cx is equal to the absolute value of C times the norm of x. So you can pull scalars out, but when you do, you pick up an absolute value. 2, you have a triangle inequality. The norm of x plus y is less than or equal to the norm of x plus the norm of y. 3, the norm is actually non-negative. The norm of x is greater than or equal to 0. And then 4, the norm of x is equal to 0 if and only if x is in fact 0. So V paired together with a norm is a normed linear space. All right. You might notice that I did not say that V was finite dimensional. We can talk about infinite dimensional normed linear spaces. In fact, I have some examples of those in these very notes. Now, so let's see here. What's an example of a norm then? Man, sad. For Rn, right? What would the norm of x be? Square root of the x1 squared plus x2 squared plus da da da. I'm going to have to stop using this. I'm sorry, guys, but I really want this to be read, but this looks very new, but useless. Let's see here. Like so many things. Could try for the, whatever. All right, so in other words, for a snazzy formula, the norm of x is the square root of x dot x, right? The dot product of x with itself, right? Or you could say x, what? XX transpose would it be? Or it would be x transpose x? X transpose X, yeah. If we want it in terms of a row column product, right? There we go. Right. Yeah, okay. So it's fairly simple to verify that this norm, which is known as the Euclidean norm on Rn, all right, satisfies these four properties. Straightforward.
And if we multiplied it by any positive number, then would it still be about
You have a homework about that, so I best not comment. But yeah. Actually, the homework is a little bit more interesting than that. Okay. Now, but before I get to the weird examples, 2, pretty much what we can do is the norm of A. You know what we can do? It's nothing more than the norm of the coordinate vector of A. That's an easy way to get the norm of a matrix. We just take the norm of the corresponding coordinate vector. And you know what? In the same way, the norm of a complex vector, norm of the coordinate vector of it. And you guessed it, the norm of a complex matrix, again, just to beat a dead horse here, right? So here I'm talking about Cn, here I'm talking about Cm by n. What's really, really cool and not at all obvious is that this is equal to the square root of the trace of A transpose A. Or AA transpose, it doesn't matter, it's cyclic, you could write it either way. This is not at all obvious that the trace is the sum of the diagonals, and that's the product of A with itself. This somehow conspires to give you the sum of the squares of all of the components in the matrix listed out. This is also known as the Frobenius norm. And this, well, this is perhaps a little bit less surprisingly the square root of Z dagger, ZZ dagger, I think. Well, yeah, Z dagger. Well, I gotta be careful. I don't know. I'm here, Z dagger is, it's the row vector Z1 conjugate, complex conjugate, Zn complex conjugate. So it's like, take the complex conjugate of each entry and then transpose it to make it into a row vector. You could, well, I'll shut up about that. And then this one, you could write as the square root of the trace of Z dagger, let's say. I mean, there's various, let me not belabor these too much. But the larger point is to define a norm on these vector spaces. In fact, what we can do is just basically take the length of the coordinate vector, and that will define a norm. All right. With that said, so there's some nice examples of normed linear spaces, all right? We got some very nice examples. And let me just take a minute to talk to you guys about the plane. And let's scratch the itch that Samuel started scratching. In other words, like, what about other norms? Is there just the Euclidean norm? Are there other norms? What's the deal? So here's some standard one for the plane. So number one, the one we already talked about, right? The norm of V is the square root of V dot V, right? In other words, this is the square root of V1 squared plus V2 squared. That's the Euclidean norm. All right, number two, again for the plane, we could talk about the so-called taxicab norm. Now the reason it's called the taxicab norm is it's hard to understand here in Lynchburg, but it's based on the idea that your net distance is the sum of the horizontal and vertical distances. So that assumes a square grid. you know, which is not quite what we have here, right? I'm not sure what the actual formula would be for Lynchburg taxi cab. I'm sorry, Uber. What am I talking about? But you need some graph. You need graph theory. It could be a master's thesis if we had that sort of thing. Let's see here. Yeah, 3. And this is actually a generalization of 2. This. Well, I'm sorry. The oh, my numbering is messed up here on page 9. My OCD is bothered. The P norm. P norm would be something like this. V sub P is the pth root of V1 to the P plus V2 to the P. So actually taxi cab norm is P equals to 1, right? Euclidean norm is P equals to 2 in retrospect. What's that? What?
Which P? Like,
The P.
or
Here P is P is a natural number. For each natural number you get a different norm. And then there's something called the sup norm, or I like to call it the sup norm because I think it'd be like sup. And sorry, it's really quite awful. But here it's the max of the absolute value of V1, absolute value of V2. This can actually be understood as P equals to infinity. Let me draw you a picture and show you why that's a reasonable statement. So, what's a circle? You say a circle centered at the origin, right? It's the set of points which are equidistant from the center point, right? Or we could look at it as the set of points which are reached by vectors of length 1, right? But the length of a vector is the norm of the vector. So our idea of what a circle is changes when we change the idea of what a norm is. Now, of course, the circle and the Euclidean norm, right? So let's say a circle is norm V equal to 1, all such V. All right? That's a unit circle in the norm, bar bar, V bar bar. And my point is, if we use these different ones, we get different things. So circle, of course, the circle, there's P equals 2. How about P equals 1? Rhombus, yeah. If I put V2 equals to 0, I get V1 equals to what? 1. So I get this point, and I get this point, and I get this point, and I get this point. Yeah, it's a diamond. In fact, yeah, that's the circle, so to speak, in the 1 norm. How about the sup norm? So we get a square, right? So the max of this and that. So if I pretty much any point here, right, has norm 1, right? See, because this is supposed to be vertical line, sorry. So this, right, these all have x coordinate 1. So you take the max of 1 and whatever, it's 1, right? And then all of this, that, like that. So this is P equals to infinity, right? This is P equals to 1. The circle is P equals to 2. If you were to study the 3 norm, it's like a blown out circle. It gets more. So what's that, a squircle? So as P goes to infinity, you go out to that sup norm.
So for the P norm, we don't need to do any absolute values?
Oh, you're right.
Them
Thank you. Yeah, you're absolutely right. Thank you. You always keep me honest. I appreciate that. Let's see here. Honesty is the best policy. But yeah, those are not optional. Indeed, thank you. Because we get odd powers, that minus can create. Yeah. No. So I know, I personally, when I first saw this, I thought, this is really neat. See, because sometimes you hear philosophers talk about the impossibility of squaring the circle. So I look at this picture and go, there it is. You just take p to infinity, there it is. Square, circle becomes square. Done, right? I know there's some extra stuff about preserving the area. I don't care. Whatever. Okay, so norm, yes. Now I have a couple of more examples in the notes which I will look at shortly, but I think I'm going to skip ahead and talk about topology. So the other examples I have in the notes are for norm of a multilinear map and the norm of like functions on a function space. To define the norm of a function, a continuous function on a closed interval, we can take the maximum of its values on the closed interval. And then in the same way, we can define the norm of a transformation, possibly on an infinite dimensional space, as like the maximum or the supremum of its values on vectors with length 1. All right? So I feel like I shouldn't talk about that right this second. I'm maybe going to come back to that when the time is right, or I may just let you read it. I'll kind of just see how the chips fall here. But so I have a couple of, like 3 more examples that are a little bit less natural examples of norms that I'd like you to read. All right?
In 321, do we define the norm of functions as integrals over, like definite integrals over certain range?
Right, the integral of a function would be example of a linear transformation from function space to the reals, and we can define the norm of that in terms of the supremum of the values it takes for you're going to break me. See here. I must seize the day and talk about topology while we have these things on the board, okay? So, what is topology? What are limits? All right. So we have this, what is a norm? I mean, the norm is the notion of distance. It's vector length, right? There's other concepts of distance and this here is actually an inner product, right? Inner product takes in a pair of vectors, it gives you out another vector. Inner products are bilinear, symmetric, positive definite maps. And yet there's this other notion of a distance function, right? Like a distance function is related, but it's not the same thing, right? Like I can use a norm to create a distance function. What would that be? Let me draw a picture here. You guys tell me how to do it. If I'm in a vector space, a normed linear space, right? And I have 2 points in the normed linear space. So here's a picture, kind of nondescript, V. Okay? I got 2 points, X. Here's another point, Y. How do I figure out the distance between X and Y in V being a norm? V is a normed linear space, right? Not just a vector space, it's a vector space with a concept of distance. So you say that this distance here is the norm of X minus Y. Does that make sense to you guys? I mean, that's certainly how we do it in Rn, right? Yeah, in the Euclidean case, that's the displacement vector that goes from X to Y. But yeah, you can prove, in fact, that if you define this function d of x comma y equal to the norm of x minus y, you can show that this gives you what's called a distance function. A distance function takes in pairs of vectors, outputs a real number, And it has some properties, like the distance from x to y is equal to the distance from y to x, right? What are the other properties of a distance function? It's what? Not, say again? Non-negativity. Yeah. Sorry, I've lost my list of properties. I must have, oh, there it is, page 12. So, yeah, non-negativity, very good. Actually, that was my one. D of x comma y is greater than, I mean, that makes sense, right? The distance between 2 points should be non-negative, right? It's symmetric. The distance from x to y is the distance from y to x. You also have a triangle inequality. So the point here that I'm making, not very elegantly, I suppose, triangle inequality. And this one has no name, but I've seen a name given to it. I forget it, though. D of xy equal to 0 if and only if what? When should the...
X is equal to 1.
Right, the distance between 2 points should only be 0 if x is equal to y, right? Same point. So you can prove, if you have a normed linear space and you define the distance function by the difference between vectors, you can prove that in fact it satisfies these 4 axioms. And so the norm induces a metric on the vector space. But the concept of metric is a much more general idea. In fact, you notice that this defines a metric, all right? And I stated it for V, but you could cross out V and put S there. S could be a subset of a vector space. It could be all kinds of crazy stuff. It could be a lattice of points, right? And if you have these 4 axioms, then it's a metric on that set. So there's no notion of linear structure or anything. And the larger problem of studying a space paired with a metric is the study of metric spaces. And this properly belongs to what's called functional analysis. So I won't go further into that, but I think it's important to note that there's also this abstract idea of a metric. There's also an abstract idea of an inner product, but we're going to focus on norms in here, okay? But I try to make these sorts of comments for breadth when I can. Okay, so let's get back to we're working towards, our goal today is to explain what we mean by a limit of a function on a normed linear space. So if you got function going from one normed linear space to another, what do we mean by like the limit as x goes to a of f of x equals to L, right? That's what I'm trying to get to at the moment. We're almost there. I don't think we need all this. So that's where I'm going, but at the moment I need to finish talking to you a little bit about topology. What is topology? If I have a set and I tell you this is a topology for the set, what do you, I mean, you probably don't have an idea what that means at this point in your education, right? Let me tell you what it means. Topology is the study of continuity in open sets. So to tell you what the topology is for a set is to say, hey, these are the sets which we're calling open. All right? So when I'm trying to describe to you the topology of a normed linear space, I'm trying to give you an explanation for which sets are open and also, yes, which sets are closed. So we need some language, which is not hard, but let's see here. So here it is. Definition. Let V be an NLS, then here we go, B sub R of X naught. This notation is probably not standard. I mean, different books have different notation. Here's the notation I'm using. But not for long, because we kind of get away from needing these details as we go on eventually. But for now,